When installing multiple current-carrying conductors in a single conduit, it's essential to understand and apply the ampacity adjustment factors specified by the National Electrical Code, or NEC. These adjustment factors are designed to prevent overheating of conductors, which can lead to insulation damage and potentially hazardous situations. Let's consider a scenario involving a 1-inch EMT conduit feeding 4 different conveyors, where each conveyor is powered by a 3-phase 30-amp breaker utilizing 10 American wire gauge or AUG wire. This setup involves a total of 12 current-carrying conductors within the conduit, triggering the need for ampacity adjustment. According to NEC tables, when you have 12 current-carrying conductors in a conduit, an adjustment factor of 50% must be applied to the allowable ampacity of each conductor. This means that the maximum current carrying capacity of the 10 AWG wire is effectively reduced by half. Now let's examine the ampacity of 10 AWG THHN wire, which is a common type of building wire, under different temperature ratings. At its 75 degrees Celsius rating, 10 AWG THHN wire typically has an ampacity of 35 amps. Applying the 50% adjustment factor, we calculate 35 amps multiplied by 0.50, which equals 17.5 amps. This means that the adjusted ampacity of the 10 AWG THHN wire, when installed with 11 other current-carrying conductors in the same conduit, is only 17.5 amps. Alternatively, at its 90 degrees Celsius rating, 10 AWG THHN wire usually has an ampacity of 40 amps. Applying the same 50% adjustment factor, we calculate 40 amps multiplied by 0.50, which equals 20 amps. In this case, the adjusted ampacity of the 10 AWG THHN wire is 20 amps. Given that the conveyors are each protected by a 30 amp breaker, and the adjusted ampacity of the 10 AWG THHN wire is either 17.5 amps or 20 amps, depending on the temperature rating used for the calculation, the existing installation does not comply with the NEC. The conductors are not adequately protected against overcurrent, and this could result in overheating and potential fire hazards. Therefore, there are 2 primary solutions to address this issue. Firstly, the 30-amp breakers could be replaced with 20-amp breakers. This would ensure that the breakers trip before the conductors are overloaded, providing adequate protection. However, reducing the breaker size might affect the performance of the conveyors, depending on their actual current draw. Secondly, additional conduit could be installed to reroute some of the circuits. This would reduce the number of current-carrying conductors in each conduit, thereby increasing the allowable ampacity of the conductors. For example, if the 12 conductors were divided evenly between 2 conduits, each conduit would contain only 6 current-carrying conductors. According to NEC tables, the adjustment factor for 4 to 6 current-carrying conductors is 80%. In this case, the adjusted ampacity of the 10 AWG THHN wire at its 75 degrees Celsius rating would be 35 amps multiplied by 0.80, which equals 28 amps, and at its 90 degrees Celsius rating, it would be 40 amps multiplied by 0.80, which equals 32 amps. Either of these ampacities would be suitable for use with a 30-amp breaker. It's important to note that the NEC specifies the conditions under which the 90 degrees Celsius ampacity rating can be used. Generally, the terminals of the equipment to which the conductors are connected must be rated for 75 degrees Celsius or higher. If the terminals are only rated for 60 degrees Celsius, the 60 degrees Celsius ampacity rating must be used. Always consult the NEC and local electrical codes for specific requirements and guidelines. Furthermore, it's recommended to consult with a qualified electrician to determine the best solution for your specific situation. They can assess the existing electrical system, perform load calculations, and ensure that the installation complies with all applicable codes and regulations. In summary, when multiple current-carrying conductors are installed in a single conduit, it's crucial to apply the appropriate ampacity adjustment factors to prevent overheating and ensure electrical safety. The adjustment factors are based on the number of conductors in the conduit, and they reduce the allowable ampacity of the conductors. If the adjusted ampacity is less than the rating of the overcurrent protection device, such as a circuit breaker, the breaker size must be reduced or additional conduit must be installed to reduce the number of conductors in each conduit. Always consult the NEC and a qualified electrician for specific requirements and guidance. The National Electrical Code provides detailed tables and guidelines for determining ampacity adjustment factors based on the number of current carrying conductors in the conduit. These tables are essential for ensuring that conductors are not overloaded and that electrical systems are installed safely. When using these tables, it's important to accurately count the number of current carrying conductors in each conduit. Grounding conductors and equipment grounding conductors are typically not counted as current carrying conductors, but there are exceptions, such as when they carry neutral current from unbalanced loads. The NEC also specifies the conditions under which different temperature ratings of conductors can be used. As mentioned earlier, the terminals of the equipment to which the conductors are connected must be rated for at least the temperature rating of the conductor. If the terminals are only rated for a lower temperature, the lower temperature rating must be used for the ampacity calculation. In addition to ampacity adjustment factors, the NEC also includes requirements for conduit fill. Conduit fill refers to the percentage of the conduit's cross-sectional area that is occupied by conductors. The NEC limits the conduit fill to prevent overheating and to ensure that conductors can be easily pulled into the conduit. The allowable conduit fill depends on the type of conduit and the number of conductors in the conduit. For example, for 3 or more conductors in a conduit, the maximum allowable fill is typically 40%. To calculate the conduit fill, you need to know the cross-sectional area of the conductors and the conduit. The cross-sectional area of a conductor can be found in NEC tables, and the cross-sectional area of a conduit can be found in conduit manufacturers' catalogs. Once you have these values, you can calculate the percentage of the conduit that is filled by the conductors. If the conduit fill exceeds the allowable limit, you must either use a larger conduit or reduce the number of conductors in the conduit. It's important to consider both ampacity adjustment factors and conduit fill when designing and installing electrical systems. Both of these factors can affect the ampacity of conductors and the safety of the electrical system. Always consult the NEC and a qualified electrician for specific requirements and guidance. Let's delve into some additional considerations and potential solutions related to conduit fill and ampacity adjustment. Firstly, consider the impact of voltage drop on the performance of the conveyors. Voltage drop occurs when the voltage at the load is less than the voltage at the source due to the impedance of the conductors. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for feeders and 5% for branch circuits. To minimize voltage drop, you can increase the size of the conductors or reduce the length of the circuit. In the scenario with the conveyors, if the voltage drop is excessive, you might need to use larger conductors than 10 AWG, even if the ampacity is sufficient. Secondly, explore the possibility of using parallel conductors. Parallel conductors involve using 2 or more conductors connected in parallel to carry the same current. This can increase the ampacity of the circuit without increasing the size of the conduit. However, the NEC has specific requirements for parallel conductors, such as that they must be the same length, conductor material, circular milli area, insulation type, and be terminated in the same manner. Thirdly, investigate the use of energy-efficient motors and drives for the conveyors. Energy-efficient motors and drives can reduce the current draw of the conveyors, which can alleviate the need for ampacity adjustments or additional conduit. Fourthly, consider the ambient temperature in the area where the conduit is installed. The ampacity of conductors is affected by the ambient temperature. If the ambient temperature is high, the ampacity of the conductors must be derated. The NEC provides tables for derating ampacity based on ambient temperature. Fifthly, carefully select the type of conduit used for the installation. Different types of conduit have different properties, such as resistance to corrosion and temperature. Choose a conduit that is suitable for the environment in which it will be installed. For example, if the conduit will be exposed to moisture or corrosive chemicals, use a conduit that is made of a corrosion-resistant material. 6. Ensure that all electrical connections are made properly and are tightened to the correct torque. Loose connections can cause overheating and voltage drop. Use appropriate connectors and tools for making electrical connections. 7th, label all circuits and conductors clearly and accurately. This will make it easier to troubleshoot problems in the future and to ensure that the electrical system is maintained properly. 8th, perform regular maintenance on the electrical system, including inspecting conductors, connections, and overcurrent protection devices. This will help to identify and correct potential problems before they become serious. By considering these additional factors and implementing appropriate solutions, you can ensure that the electrical system for the conveyors is safe, reliable, and efficient. Remember to always consult the NEC and a qualified electrician for specific requirements and guidance.